Good afternoon. So, anyone with any questions? So, I sent some of you emails about items which were out of stock. So, as you request items, it's extremely important that you check there with the vendors because otherwise, a several day latency by the time the vendor gets back. The other thing is on the spreadsheet, you would see a line saying items up to this point ordered. If you're going to change anything, make sure it happens below that line because I'm not going to look above that line. And better yet, if you are adding anything to the spreadsheet now, drop me an email because I do not get any automatic notification when stuff gets added. But there were 3 or 4 items where there were snafus, but I think most of the other stuff should hopefully trickle in during this week. I'm going to be out of town Thursday, Friday, and Monday. So what I'll do is to have a couple of my students periodically check my assistant's desk and fetch stuff to the lab. And as things come in, I'll inform you guys. Now the thing is, they're all jumbled up because there were like multiple requests for Raspberry Pis and stuff like that. So there'll be a sign out mechanism again. So my designated students for this thing are going to be Amr and Bo. Some of you might have met them, but so I'll inform them, but basically you'll be collecting from them. So I'm hoping that much of the stuff should trickle in this week because we ordered by 2-day UPS. So unless things are out of stock, I think we should see them. Any other anyone still hasn't entered stuff onto the spreadsheet but plan to? What are you planning to order?
A purchase order for a digital blueprint.
For what?
A blueprint, just an AutoCAD file.
So, like you want to?
We're doing feature extraction on blueprints.
Oh, so you just want some blueprints?
Yeah, one digital blueprint.
Okay. Okay, that should be straightforward. Yeah, just again, please make sure to check because remember, my assistant has zero technical knowledge, so she cannot substitute anything or even hunt for equivalent parts. Okay, so things will just stall in the pipeline. So just make sure of that. Okay, the other thing is, as I said, I'm not going to be here on Monday. So, and also this Thursday, Friday, so that's 2 implications. Number 1, I won't have office hours this Friday. If there is something really, really important, then come and see me on Wednesday during the office hours. I'll do a makeup of office hour next week, maybe Thursday. That's one thing. The second thing is the Monday lecture would be on Android architecture as well as how to write Android apps which work with sensory data. Some of you are already encountering it in your projects, but it would be useful for others just educationally. So that will be given by Bo, whose name I mentioned a short while back, and Mustafa, who's another of my students. They've given this lecture a few times in this course in prior years also, so hopefully it's a smooth enough presentation at this stage. We are updating it a bit for the latest releases of Android. So, and Wednesday lecture is going to be as usual. Okay, so last time we had started looking at one of the ways in which you could parcel out resources, a processor or any other shared hardware among multiple tasks with a particular model, one where tasks have deadline and we want to make sure that the deadlines are met, except in this case the notion of deadline is really tasks are periodic and we want to make sure they finish before the next copy of that task arrives and have a bunch of such different types of tasks. And I kind of made a few points. Number 1, that in the static scheduling paradigm, which is by far the most common one that you would encounter in operating systems, tasks have priorities. Operating system makes the promise that at any given point in time, the highest priority task is running. Tasks change state because events happen. So either external events or currently running task does something like produces some piece of data which the other task was waiting upon. In a commonly used case, the task can be preempted. That is, as soon as a higher priority task gets ready, the OS kind of jumps in, stops the currently running task, saves its state, and starts the new one. So in that paradigm, then one sort of initial theorem I had a few slides ago was that to find the worst case situation for a task, you only have to look at the situation when it arrives, a copy of that task arrives, um, and simultaneously with a copy of each one of the higher priority tasks. That's the worst case. And remember, priorities could be assigned in any order you want. But the second result was that the optimum way of assigning priorities is, in this particular situation, is by their rate. So you assign the highest priority to the highest rate task, or in this case, it's the same as saying the task with the shortest deadline. And what this says is the following, that if this assignment cannot schedule, then no other assignment can schedule. Okay, you can shuffle things around, it will still remain non-schedulable. So if you have independent tasks which are periodic with deadlines equal to period, then really you got to test only for the case that it is rate monotonic. If you choose not to have rate monotonic for whatever reason, some other priority assignment, then you will revert back to that check for each task that for its worst case arrival, it meets its deadline. Then another result we had was that checking by this worst case arrival time is kind of painful. It's pseudo polynomial time complexity because you essentially simulate. So there's always been a hunt for quicker ways of testing schedulability, so that when an application asks for a new thread to be activated, you can quickly check, can you let this thread in or not? Can you let this process in or not? So one early result was that if I know utilization, that is, if I simply sum up what fraction of the CPU is needed by all these tasks together, ignoring any deadlines and all, so simply computation time divided by period, sum it over, then if it is less than equal to this expression out here, then where n is a number of tasks, then we are guaranteed to be schedulable. And if it is above that, but less than equal to 1, then it may be schedulable. If it is greater than 1, of course, it's not schedulable, assuming it is a single processor. Separate result is if n is taking n limit to infinity, this expression converges to natural log of 2. So that's basically saying I can take an arbitrary size task set, and if its utilization is less than log 2, then it's certainly scalable. Now, the problem here is it leaves a lot of slack, in the sense there are lots of task sets which are schedulable, but this thing will give you an answer which is it doesn't know, because there's a big range where it really can answer that. In fact, you can easily imagine that I can create task sets which are such that their utilization is equal to 1. They need the entire processor, and they're still schedulable. Trivially speaking, just imagine I have 2 tasks which are both periodic. They take 50% time each, and their deadline is just arranged to be right, that you can fully schedule it. In fact, there is a theorem which says that if I have a set of tasks such that one task's period is a multiple of another task, and they're all like this, they're harmonic, that is, say, period 1, 2, 4, 8, something like that, then they're always schedulable. So this is a very loose bound. I guess that's the long way of what I'm trying to say. So, but nevertheless, it's a useful result. And I'd walk through this example that we had this task set where you calculate u, and it's 0.41, and for n equal to 2 case, it's comfortably less than the limit, so it's schedulable. We add a third task. In that case, the u becomes 0.86, and it's more than the expression, the threshold we have for n equal to 3, so therefore it may be schedulable. And now you have to do the longer test. So we do the deadline test for task number 3, and it turns out that it indeed is schedulable in this case. There's a better result which appeared in early 2000s, and what this says is that if I knew the u sub I, that is, for each task I know the fraction of the CPU it needs. Remember, the previous expression only depends upon knowing the total U, okay, for the whole task set. Here, if I knew the individual UIs, then if this expression is met, namely UI plus 1 product across all the tasks, if that's less than equal to 2, then again the task set is schedulable. And this one is a less pessimistic test. In fact, in a lot of common cases, it does extremely well. So, I guess this is probably the preferred test to apply. It's again the complexity is just order n, so it's good. But let's say it fails, or let's say your priority assignment, for whatever reason, you want it to be non-rate monotonic. Maybe for some reason, and we'll see some reasons later on, you insist that priority assignment is not rate monotonic. One very common reason may be that you have some task bound to an interrupt, and the interrupt is the highest priority task in a system because that's how hardware is designed, but the rate is lower. So it's in that case, it's as if I have a task set where I have deliberately not given the highest priority to the highest rate task. To be able to analyze those, you would need to conduct that simulation type thing on an arbitrary task set. So you can structure that a little bit nicely as well to be able to write, put it into a nice algorithmic form. And the way it works is the following, that we'll come up with an expression for response time for a task. So a task arrives at its worst case instant, and we are going to see what its response time is, and it's going to be a recursive expression, and then we are going to solve it iteratively. So let's say we call the response type of a task to be R sub I, okay? If I look at the highest priority task, then whenever it arrives, it will grab the CPU, and therefore its response time is going to be simply its computation time. So R will be equal to C for the highest priority task. If I look at other tasks, then when they arrive at the same time, when they arrive in their worst case situation, then some of the time will be eaten up by the highest priority task. So if we look at the response time for a general task, so R sub I, then it is going to need computation for itself, so that's C sub I, and then also it would need I sub I, which is sort of this term, and that is the interference coming from all the higher priority tasks which are going to bump it off, okay? So whenever they are ready, they're going to grab the CPU. So we have to figure out a way to compute this I sub I. And our goal is that once we solve for the response time, then if we can show that the response time is less than the deadline, then I'm good to go. So to calculate the response time, look at all the tasks which are higher priority. Okay, so let's consider a task J, which is higher priority than I. So, and that J task has some period T sub J. So now if you think about it, how many times this task is going to arrive during this period? Well, it is going to be the ceiling of whatever my response time is divided by T sub J. Okay, so I remember response time is unknown, so but it is going to be something. So response time divided by the period of the jth task, the ceiling of that. And remember, there was a copy which came right at the beginning, so we are counting from that. So the number of releases of the jth task, not k, of task j would be this much. And each time it arrives, since it's a higher priority task, it's going to run to completion, right? Because it grabs the CPU. So the total CPU time it will need is going to be this term. So again, the R sub I divided by Tj, the ceiling of that multiplied by C sub j. So that's the interference from a high priority task. And then the total interference is going to be summation over all the tasks which are higher priority than I. So we just call that set to be HPI. So HPI is the set of tasks which are higher priority than I. So I kind of sum them over, and that gives me the total interference that the ith task is going to see. Is that clear? Right? We're just kind of adding up how much time each one of the higher priority tasks is going to take. And that gives us this equation. R sub I is C sub I plus the sigma term. Remember CJ, TJ, CI, they are known. RI is the only unknown out here, so we have to calculate this. This is a classic expression fixed point type problem, x equal to fx, where in this case f is highly nonlinear, so you are going to nonlinear simply because of the ceiling function here. So usually the way we solve this thing is that we start with some assumed value of x and work from that. Now we have a very reasonable starting value for r sub I, which is c sub I. We at least are going to need as at that much response time. So a reasonable starting point for r sub I is simply c sub I, and then you iterate on it. So this is the iteration equation, n plus 1, basically n and n plus 1 indicate the iteration number, and at some point one of the two things will happen. It will either converge or it will violate the deadline. Okay, now remember, at every iteration we are only increasing, right? So if I start with some value of r sub I, it's going to kind of increase, and at some point either wi n plus 1 will equal to wi n. That means we have converged, and that's the value of r sub I. Or alternatively, I will reach a value which exceeds the deadline that we have in mind, which is t sub I, and therefore, or anything else, any other deadline you have, in fact, and then we can kind of stop there. Okay, so easy way to solve it. There is some pseudocode for kind of arranging for this thing, and this again, this is effectively doing that simulation. I mean, if you think about it, we are really accounting for everything out here, and the time that you would take is going to be proportional to the deadline that you have in mind. I mean, so you have to simulate for that long, basically. So it's a straightforward piece of code. There are, if you just blindly follow it, you'll always obviously get correct results. Oftentimes what happens is people kind of start doing other forms of intuitive reasoning around these things and often kind of go awry. So one very common mistake that I have seen is I give you a bunch of, you're given a bunch of tasks, and you would basically just go after the least priority task and show that it is schedulable, and then you would say, aha, and therefore the whole task set is schedulable. And that is not true, because it could be that the violation, actually your bottleneck task could be something in the middle. So you really have to test for every task. You cannot skip that step. Okay, so that's extremely important. Another another sort of mistake that I've often seen is that the test that we had put, that original expression, oftentimes sort of people apply this. They basically say computation time plus interference time is less than equal to t sub I. The problem is it's sufficient test, but it's not a necessary test. If you kind of think about it, so it again kind of gives wrong results. You can use this kind of an analysis in a loop to play all kind of games. So like, for example, let's say you're trying to figure out, can I how fast a processor can I have? Okay, let's say you find your task set is schedulable. Then you say, could I run it on a slower processor? How slow can the processor can be? Or other way around, if the processor turns out to be non-schedulable, so you want to ask, like, what's the next frequency that it will work at? So you can think about that as, if I change the clock frequency, then all the C's get changed, right? So my deadline remains unchanged, because deadline is whatever it is. Period remains unchanged, because that's again dictated by the external world. But the one thing which does depend upon the processor is the CI terms. So you can always create a hyperparameter around this, which is the frequency of the processor, and you are going to be given the computation time for some frequency. And now if you change the frequency, then you multiply all computation times by that alpha term, and then you can recompute. You can go fancier. Oftentimes it could be that for different tasks, you may run the processor at different speed. So when running task number I, processor is running at some speed number I. Let's say you want to have that flexibility. Then again, you can kind of use this thing in a loop to kind of work around it. There is a more direct way to kind of reason about these constraints, but you can always use this thing as a function and kind of reason around that. Let's see. Okay, a more direct way of thinking about this is the following. Sorry for jumping around. So let's imagine again I have a bunch of tasks, task 1 to n, and task 1 is highest priority, task n is lowest priority. And now if you think about what does it mean for task I to be schedulable, then a necessary and sufficient condition is that somewhere during the period from 0 to the deadline, so 0 to ti, there exists some value of t where the following condition is met, which is t is greater than equal to all the computation I need. Okay, so if you think about it, what's happening is there's a competition between two notions of time which is taking place. There's a wall clock time, which is advancing at its rate, the universe rate. So that's t, and then I need computation. And every so often a new task arrives, and that requires, and it's a higher priority task because I'm looking at task size, so it's a higher priority task. So I need computation for that. So each one of these terms that you're seeing, which correspond to the ceiling, is corresponding to the work needed by the higher priority task. So really my expression is that I want to find, does there exist a t within my interval of interest such that t is greater than equal to this expression, because if that is met, then my task would be schedulable. So it's really hunting for t is what we are after, and since we are looking over a continuous interval, you would say, okay, so I have to hunt for all values of t in there. But if you think about this, the right hand side only jumps whenever one of these ceiling terms changes. So that means that the only values of t which are of interest to us are those which are multiples of one of the periods. So my search problem is now limited to all those values of time which are multiple of one of the periods of one of the higher priority tasks. So with that, you could write the set of constraints slightly differently. So you can say the work I need is equal to the work needed by all the tasks which arrive during that time t. And here I'm also including the ith task, so the task under consideration. Then I can define this ratio between the work I need, that is the CPU time I need, divided by the real time that has passed, so that's Li of t. And then what I'm looking for is that what is the minimum value that Li of t takes during the period of interest to me, and across all possible tasks I, and then I'm going to look for the highest one out there. Let me try back on this. These two are a little confusing. But remember, our constraint is that the real time should be equal to more than the computation time that I need. So what we have is this ratio, work divided by t, and I'm really looking for this guy meeting some particular requirement. So for ith task, as long as there exists a t such that this ratio dips below such that this ratio meets the work requirement, then I'm good to go. So uh, a general sufficient and necessary condition then is that given a task set, ith task is schedulable if and only if L sub I is less than equal to 1. That is, there exists some value of t where I was ahead in terms of wall clock time. And then I can check for all tasks to be schedulable, all the LIs should meet the requirement, or another way of saying is the highest of them should still be practically speaking, as I said, we only need to compute at all times which are multiples, because that's when the task sets are released. So rest is kind of algebraic mumbo jumbo, but main thing really boils down to is if a task set is given, then you can compute all the multiples. So like for example, if I'm looking at task 1, then the multiple of that is really just going to be 100. If I'm looking at task 2, then task 2, I have to check at 100 because task 1, which is high priority, can come at 100, and then 150 for task 2. and likewise for task 3 and task 4. So I can identify the sets at which I have to check that work condition, that is CPU time needed divided by the real time should be less than equal to 1. And so you can plot these things, and a task is schedulable if any part of the plot falls on or below the diagonal line. Okay, so we just want somewhere in our period of interest there should be at least one value of t where we kind of fall below this thing. You can translate this thing into a whole set of inequalities. So you can basically say since wi of t only changes at values in the set. So I can basically say that, let's say I'm looking at task number 3, then I really have to say that at one of these 4 values, the condition, the li of t should be less than equal to 1. So each one of these is going to correspond to an inequality, and we have to make sure that one of them is true. And so for each set, I have to make sure that one is going to be true. So oftentimes, in many cases, just in terms of logical reasoning, this turns out to be a much easier way to do it, because you can look at it and say, what is my constraining task like in this example? What I've done is I've jotted down all the inequalities that result, and what I've also done is in the red I have shown the one which are violated, and in the so like for example, if you look at this one, W300 equal to 130, so which is basically saying that at t equal to 100, I needed 130 units of computation time, and therefore it's violated. On the other hand, let's say you look at this last one, W3210, it needs 200 of computation time. So what needed is 200, but I had time to 10, so I'm good to go. So each one of these clusters, for each one of the tasks, I should have at least one green inequality saying I met. So in this case, you can see that task 4 is problematic because all its inequalities are red, they're all violated, and therefore I need to boost up the CPU speed. Now, one thing you can look at it and say, I'm already meeting the timing requirement for task 1, 2, and 3, and so I don't need to have a higher speed CPU when they are running. And maybe I only need to speed up the CPU when task 4 is running. Okay, so in this case, for the lowest priority task, I can bump up the thing. Or alternatively, I can globally speed up the CPU, in which case these guys will have even more slack, but perhaps I'm wasting some CPU power. Looking at these inequalities, you can begin to see that how much do I need to speed the CPU by. So let's say I look at W4 to 10. It needs CPU time of 300. That means in time 210, currently I have 300 units of computation time.
The numbers in the brackets, those are all the different tasks you need to do.
Okay, so the 4 cases are the 4 tasks. These numbers in the bracket correspond to the multiples that exist. So I'm looking at W4T had T4 of 400. So I am looking at all the tasks, all those times at which some task was released. Okay, and so in 400, I would have possibly T1 released at, I'll have T1 released at 100, 200, and 300, and 400. I'll have T2 released at 150 and 300. I have T3 released at 210. Okay, so I have all those cases because, and that was coming from because the term in computation time jumps every time a new task arrives. So I have, if you look at alpha 4, has all those entries, 1, 2, 3, 4, 5, 6 entries, and therefore the entry for the 4th task has 6 inequalities, 1 for each one of them. And I have to make sure that at least one of those inequalities in each group is met.
So in a more practical setting, you would look for, I guess, the one that is closest to its...
Yeah, you look at the ratio. So you look at ratio 400 to 430, for example, the last one, right? Because that's the ratio tells you how far apart we are, and that's the percentage speed up that you have to do.
Okay, and another way to do it would also be to improve the C's of one of the tasks as well.
That's what we are doing, right? I mean, by so let's say so let's look at so we are good on the first 3, right? So we are just looking at the 4th one. So the first inequality says I had time 100, but the computation time needed was 230. So I need to improve the CPU speed by a factor of 2.3, right? And that will speed everything up, and then I'll be good to go. Second one is saying I have time 150, and I need CPU speed of 250. So it's 250, so 25. So it's the speed of is 5/3, which is 1.6666, right? So I'm better off than 2.3, and so on and so forth. I guess staring at this thing, it would seem to me that probably the last one is the best one. Most likely 430 over 400. So I need to speed up by 1.0 something. Yeah.
So in this example, task 1 needs to do one process that takes 20 units.
And it's the highest priority task, so it's already to go.
And then task 3, say, is
task
the task
3
that takes 80 units.
Task 3 needed task 3 needed 80 unit, and it had time to 10 for doing that. But during that time to 10,
And they're all
other stuff.
periodic, so
Yeah,
they
they're
happen
periodic.
again and again.
Yeah. Any questions?
What I was talking about is those C's that you have listed there, like say you don't have, like, you already are at max processor capacity, you would then have to look for, like, minimizing the C somehow, like improving the code or.
Oh, okay. If you're already at the max highest
Yeah.
speed processor, then somehow you have to resort to algorithmic means to improve the C. Yes. Okay. Generally speaking, yes. There is one other trick, which is the following: you split the tasks. So it turns out that, let's say I have a task which comes every 100 time units and needs 40 time units of computation time. Maybe I can split it to a task which comes every 50 time units and takes half the time. So I have part A, part B of the task. If it comes twice, takes less time, and it turns out, we'll see later why it helps, but remember a short while ago I said that that there is a theorem that if task periods are harmonic, and if the total utilization is less than or equal to 1, then they are always schedulable. So I can, in theory, take up a set of tasks and divvy it up really in final granularity so that all of them have the same period. Right? I could do that. Conceivably, it would be awful from a software engineering perspective and keeping track of everything, but I could, as a theoretical exercise, do it and then make the task set schedulable artificially. But you would really not do it, because dividing up a task at that final granularity so that they all become harmonic is extremely painful. So generally speaking, therefore, we will try to improve C algorithmically. Yeah, and so you really have two knobs, right? Reduce C for a given frequency, change frequency. The other thing to bear in mind is, like, if you look at this example and others, it's very common that you will end up a situation where your processor utilization is much less than 100. That is, if you do sigma Ci over Ti, but the task set is not schedulable. Okay, in this case, you can see that's probably the case, right? So first task is 20 over 100, so that's 20%. Next task is 30 over 150, so that's another 20%, so we are at 40%. Third is 8 over 21, so it's less than 1/3, so we are not even at 70% yet. And then finally 1/4, so this task, I think, is somewhere around 0.9 or something like that processor utilization, but it's still not schedulable. Okay, so and the problem is the deadlines. Because of the deadlines, I have to over provision the CPU. I need more CPU than I would need because to meet the deadline, right? So intuitively, if I have a task whose deadline is very aggressive, then it requires me to be faster during that time, basically, and that's what's sort of going on here. Actually, let's see what was going on. Yeah, in this case, I did play some other game, but okay, I have to see. So, so what we've seen is that really the golden test really that you can apply, which will always work, is to use this response time analysis. The nice thing there is that you can work with arbitrary priorities, not just rate monotonic. And the second thing is you can also actually work with deadlines which are less than the period, because the same thing kind of applies there. Whereas those efficient tests I gave you, the u less than equal to nth root of 2 minus 1, or the other one which was the harmonic test, product of ui plus 1 being less than equal to 2, they only work when you do a rate monotonic assignment. And a generalization of all of this is that if my deadlines were less than the period, as opposed to being exactly equal to the period, then the revised revision of the theory, which came in late 90s, is called deadline monotonic. So it's a very simple generalization, so not worth spending much time over. But basically, a bunch of tasks, I have periods, but previously my deadlines were always equal to the corresponding period. But now I have deadlines which are smaller than the period. Okay, so deadline of 5, period of 20. And in that case, the theorem which emerges is it says that deadline monotonic is optimum, which means that if I assign priority according to these deadlines, in this case task 1 having the highest and task 2 the next and so on and so forth, whereas rate monotonic would have said that task 3 should have the highest priority, but deadline monotonic says task 1 should have the highest priority. So if in the case of d less than t, deadline monotonic is optimum. That is, if that priority assignment doesn't work, then nothing else will work. You can no longer, in case of deadline monotonic, you can no longer use those expressions, the u and the product of ui plus 1, because they only apply to rate monotonic, but the response time analysis still works. So the only thing is, in response time analysis, you are now going to stop at the deadline. That's your constraint. The rest of it still works. So yeah, so that's deadline monotonic. One other, some other issues that kind of come in practice. So I'm going to kind of walk through them bit by bit. So one issue that you often face is that this notion of priority that we have doesn't always necessarily map to importance. So remember, priority in our case is driven by deadline or by period, but there's nothing that says that my highest rate task is the most important one. Like maybe on a car, the highest rate task might be the one processing the LiDAR or radar or something like that, but the most important task may be the one which controls the brakes. Okay, so you want to make sure that the importance versus the rate are not confused. So now the thing is, when everything is going fine, it's all okay, all deadlines are being met, so who cares? But the problem comes that occasionally the processor comes under load. And when I say processor, I'm really saying whatever resource you have, right? So the processor, if it's really a CPU, it can come under load because maybe there was more interrupt traffic, or maybe because temperature is hot and therefore the hardware regulates that temporarily brings down the frequency. Or maybe your processor is a radio and is sending traffic over a wireless channel and there's a lot of noise on the channel and therefore the rate plummets. Or maybe you're simply just far away from the nearest access point and therefore the rate goes down. So we encounter these situations where there are transient reduction in the server capacity, and therefore it's as if that my overall processor, instead of having 1 unit of computation time, like remember we always say u less than equal to 1, that 1 instead of being 1 is now varying. Okay, yeah, it can go down, so yeah, I have to somehow sort of take care of that. Now the thing is, when the processor capacity goes down, in a static priority case, which task do you think will miss its deadline first? The lowest priority one, right? Because it has the lowest priority. So, but what may so basically the whatever processor resource we have, we first give it to the highest priority one, right? But that may not correspond to our criticality. So in this example, artificial example, I have task 3, which is third in priority, is the one which is non-critical, and task 4, which is lower priority, is critical. So what we want to do is, if there is ever any transient overload, I somehow want to make sure that 4 is prioritized over 3. Okay, but purely from a deadline perspective, 3 gets the priority over 4. So could we somehow sort of deal with this issue? So I'll just show it by way of example, and this kind of goes to this splitting the task business that I was talking about. So I'm simplifying the example further. So let's say I have two tasks. Task 1 has a period of 10, task 2 has a period of 14, and they have the computation time as shown, and they have deadlines of 10 and 13. So in the deadline monotonic kind of a framework, the second task will have the lower priority. But let's say the second task is a more critical task. So if there is ever an overload, I want task 2 to go through before task 1, right? So now in this case, if I make task 2 the higher priority, you can easily show that it's not schedulable. So while I do have, when I have the full processor available, if I were to simply give task 2 the priority, then it won't work. So my only other solution would be to use a very fast processor, right? One which even with this alternative priority assignment still kind of works out. So that's one option, but then I'm paying for a costlier processor or burning power kind of all the time. So a better approach is the so-called period transformation. And the way it works is the second task, remember the one which had period of 14 and computation time of 7, what we are going to do is, and it had a deadline of 13, what we are going to do is we are going to split it into two parts, part A, part B. So just imagine the task had a function, and somehow magically I'm able to divide it evenly into two halves. First half, we are first half and second half, each one of them will have computation time of 3.5 because we divided them evenly. Their period is going to be 7 because now if you think in terms of these parts, they are coming more frequently, right? So for this modified task, the period is 7, computation time is 3.5, and if you think about what's the deadline, well, for one of the parts the deadline is 7, but for the next part, the alternative one, the deadline is going to be 6. Remember, we have to finish by 13. So what we really have to make sure is that every whatever even number part starting from 1, every even number instance finishes in a deadline of 6. So we really have to set the deadline here to be 6. And so it's the same task set. The only thing we did is the software engineering game of splitting it up into 2. And now, as you can see in this case, the period of task 2 is higher. And now my period and criticality are aligned, and this thing will work. This thing will meet its deadline and will also meet its criticality requirement. That is, if the processor slows down for whatever reason, task 2 will get to, task 2 will be preferred in terms of not missing a deadline. Of course, if the processor slows down a lot, then you can't do much. But if processor slows down somewhat, then task 1 will be the first one to miss its deadline. So this approach of doing period transformation or this splitting of code is kind of a powerful tool because it improves schedulability, but it comes at the cost of this ugliness, namely you have to split the code, which can be hard because if your algorithm is iterative, and how do you even estimate where exactly is the halfway point? I mean, these are all estimating the delay through a code is pretty tricky, and there are all sort of caching effects and things like that which you will encounter very, very readily. So in theory, this is nice. In practice, kind of takes some effort to get it to work. But taken to the extreme, you can actually use this transformation. If you can, using this transformation, if you can arrange for periods of tasks to become ratios of each other, become harmonic, then you can improve your schedulability all the way that as long as utilization is less than equal to 1, you are good to go. So in this particular case, if I look at this, two tasks, first task has a utilization of 50%, and next task, period of 15, so lower priority, has a utilization of 1/3. So it's 83.33%, and it turns out, if you work it out, then just schedulable. That is, if you increase either C1 or C2 even by a tiny amount, or alternatively, if you slow down the processor even a tiny amount, then they will miss the deadline. Okay, so they are exactly just schedulable. On the other hand, if I transform this task, the first one, I split it. So it has two parts, and so each part will be of size 2.5, but now the period becomes 5 instead of 10. If I look at this, now if you try to schedule it, you can see that the utilization bound is 100%. That is, I can keep slowing down the CPU, and all the way until, so if I slow down the CPU, these will increase proportionately until you become exactly 1, and then it will still be schedulable. So I have sort of, well, here I did not have the ability to exploit that slack. Here I can exploit that slack.
In this one, does it mean that the first task has to be scheduled every 5 units and it takes 2.5?
Right.
But if the
But
second task,
except that alternative parts are part A, part B. Right? So, because remember, I split the task now. So what's happening is here, I have this new task which is coming every 5 time unit, except, or let's say, first time I'm going to run part 1. The next time it comes, I'm going to run part 2.
What if
part 1, part 2?
task 2, so it has 100% uptime because task 2 takes 5 time units.
No. So this doesn't. This thing is still the utilization of this thing is still 83.3% because this is still 50% and this is 1/3. So that's 83.333. Right. So that's still what I'm saying is utilization bound, and what that refers to is that as I now slow things down, or alternatively as I start adding, right? I mean, if I let's say increase C1A to 5 and increase C2 to 50, you would see that it's still schedulable. Okay, whereas here, if I increase either one of these even a tiny bit, it will no longer schedule. So here it's just schedulable, and here I'm actually able to make use of all the slack. I have a lot of it. So this period transformation can basically create flexibility where previously there wasn't any. And the second case, you would see the ratios are harmonic, 5 and 50, so it is multiple of the other. And anytime you have periodic tasks where you have this kind of a nice ratio, that is, if I were to just go from fastest to slowest task, they just form a ratio of 1 is to K1, K2, K3, something like that. Then you can go all the way to 100%. So, yeah.
So how do we take into account, for example, let's say you have a simple embedded system that has 2 tasks that are harmonic in their periods, and the utilization is way under 100%. So let's say you have, they're doing something that's time sensitive, for example, like let's say ADC sampling. And if they're harmonic, then they're eventually going to overlap. If you start them both at the same exact time, they're going to be overlapping in this case every 3rd time.
Yeah, but remember the deadline is able to do it, right? So in this case they do overlap, right? I mean, so what will happen is that the promise we are giving is I'm going to finish you before the next time you arrive.
So if you have to take, let's say, a sample at the same exact time, and you're
No, so again, bear in mind what is the promise we are making, right? We are not saying where, since you arrive, all the promise we are making is when you will finish. We are not saying we are not giving any promise about precisely when you will execute. So if you are asking for that promise, and I can see in some cases that you do want that promise, right? That is, when I arrive, then I want to execute right there and then. Then basically you are saying that task is the highest priority task. And since I can have only one task which is the highest priority task, I can make such a promise to only one task.
So basically, in this example, you solve that by giving 15 time units to solve it. So sometimes you'll solve it in the first 5, and then sometimes you'll solve it in the last 5.
And sometimes it will be split. I'll run 1 and then wait and then 4, right? All I'm promising is that you will get your 5 units within those 15 since you arrive, right? That's the only promise that you're getting. So what Leon is asking for is, I cannot tolerate any jitter. That's basically right.
Yeah.
It has to. Then really the only thing is that task has to be the highest priority task.
Well, what about just like staggering them? Like my idea was just like you give them like some delta. You don't care that they have
in
to
this
get that
in
exact
this
time.
framework you cannot. So with these kind of operating systems you cannot. So the alternative way is indeed what you are saying. That remember that's the cyclic executive kind of a model that we had, where we laid down frames and slots and we assigned things into the slot. So then I can tightly control things. Okay, so that would be in communication terms. That's the time division type, time division slotting. I really lay it out statically. So that's you would have to go. So that's the other paradigm you can work with. But then it comes at a cost that everything is rigid. Okay. But this kind of a model where OS can preempt you anytime, that promise that you are seeking can only be made to the Any other questions? So the splitting is useful, but one has to do it carefully because um, it is uh, it just makes your code ugly. Okay. Other concepts that get used out there. How do I handle sporadic tasks and these things? Right. I mean, all framework is around tasks always arriving and stuff like that. So what about tasks that are don't have a period associated with them? How do we deal with these kind of things? So a very common approach for doing this thing is the following: that I will create a fictitious periodic task. Think of it like a server, and every period, because it's the highest priority task, is going to grab the CPU, and what's going to do is it's going to check: is there any sporadic task sitting in the queue? So as sporadic tasks arrive, we are going to put them into the queue, and then during this time period, I'm going to serve them. And if it turns out that no sporadic task arrived during that present time interval, then I'm going to release the CPU. Okay, that's one model. Another one is basically wait, see if something arrives. So sporadic tasks essentially get bundled up and handled into this um,
So what if they take more time than the allotted time there?
what if they take more time than is the allocated time? There depends on the type of scheme how you arrange these things. A common one would be that you defer them until next time, so you kind of stop them, and then when put their state back into the queue, and the next time again. Another one is that if nothing was ready at the time the server became it was time for the server, then instead of losing that time, you kind of accumulate it so that you can recoup it later on. So these are all nuances. Main thing is the reason these kind of schemes exist is because for these are the ones for which researchers were able to come up with theories which were still able to maintain deadline promises for everything else. Okay, so see what's happening out here is that in the first case, it's very nice and clean. So as you might imagine, all the other stuff which are fighting over for the remaining white space, you can still make some promises about it. So there are papers which kind of give you the formula and all. This one relaxes things slightly, namely I can still recoup it later, and turns out even with this case, you can still make certain promises. So a lot of these models that you see in literature, they exist primarily because the schedulability test for them exists. That is, given them, you can still say, oh, can I still schedule them or not? Next up, so thus another assumption that we had made early on was tasks were independent. They were not talking with each other. So it was never the case that one task is waiting for something from the other task and therefore cannot run, right? All tasks, runnability requirements were independent of each other. But that's not going to be the case on most systems. So in most systems, tasks interact, they share data, they share resources, they may both want to use the same serial port or the same radio, or perhaps they talk to each other using a queue or something like that. So operating systems give you all sort of abstractions to deal with these kind of things. So if you've done any multi-threaded programming, you would have heard these things like semaphores or locks or monitors and stuff like that, or even queues and all. So anytime you have anything shared, you have to deal with the fact that somewhere deep down, I have to cause one process to wait for the other. Okay? So, and likewise for something like radio, if I'm sending packet over the radio, so I'm going to lock the radio, and the other task using the radio has to wait for it. So fundamentally, anytime you have this kind of constraint, then you have a problem with timing constraints. In fact, previously we talked about that a task can be interfered by a higher priority task. But in a situation like this, a task can be interfered by a lower priority task, right? Imagine two tasks for sharing a resource. Task A is higher priority, task B is lower priority. Task B grabs the radio, and now task A wakes up because the sensor reading arrived. So task A got the CPU, it wants to run, and it now needs the radio, but the radio has been grabbed by task B, right? So in this case, now we have an interference problem from a lower task. Now in some cases, maybe task B can release the resource immediately, but usually that's not the case. It may be in midst of doing some operation, some computation. Somehow we have to account for the sharing going on. And it turns out that if not handled right, this can really mess things up. And there are plenty of examples of in real life where this thing has happened. So this problem is called priority inversion, and basically what I described is what happens intuitively. So what's happening is there are three tasks in our system. Task 1 and 3 share a resource. Task 1 is higher priority. Task 2 is an intermediate priority task, which does not share any resources independent of these tasks 1 and 2. Now let's imagine task 3 grabs a semaphore. Semaphore, those of you don't know, is a abstraction that operating systems provide, which is how you lock resources. So like whenever you want to use a resource, you kind of lock it. So it's called locking the semaphore, and when you're done, you kind of release it. And deep down, the OS makes sure that it never happens that two entities can simultaneously lock a resource. Okay, somehow using hardware or software or ensures that. Okay, that's all that matters for our purposes. Somehow such a semaphore exists. So task 3 uses a resource, and so it puts a lock on the semaphore, and then it starts doing its critical stuff on the shared resource. Meanwhile, task 1 becomes ready, and task 1 therefore preempts whatever was running. And now task 1 attempts to use the same shared resource. So task 1 tries to use the shared resource, but its shared resource is taken by 3. So intuitively, it stands to reason. You will say, okay, let's give the CPU to 3 because that happens. But now imagine task 2 arrives. Since task 2 is higher priority than 3, so task 3 cannot run. And since task 3 cannot run, the resource cannot be released. And since resource cannot be released, task 1 cannot run. Right? So task 2 arrives. And let's say task 2 keeps arriving. So task 3 will progress very slowly. And therefore, task 1 may have to wait for a long time, right? Potentially a really long time, and therefore misses deadline. So, so one has to somehow manage this situation carefully. Intuitively, what you would like to do is that task 3 should get treated as if it's task 1 for that period, right? Its priority should be equal to that of task 1 because it has blocked a high priority task. But if so somehow we have to manage that. Otherwise, task 2, which is intermediate priority, will grab.
Wait, so, sorry, I got confused a little bit about that part. So T3 has to lock, and then T1, sorry, T3 has the shared resource to lock. T1 is lower priority.
No, T1 is higher priority. T1 is the highest priority. T3 has locked the resource. T1 wants the resource, but T2, which is intermediate priority, keeps coming.
Oh.
Okay, and therefore it's preventing T3 from proceeding, and meanwhile T1 is waiting. Okay, so what you want to do is to somehow kind of treat task 3 differently.
I'm just curious about why do you use semaphore in this specific case instead of using mutex?
You can use anything, mutex, lock, the same thing will hold true. In fact, the only reason I'm using semaphore is because it's usually the common abstraction for resources, but deep down you're right that everything, the core primitive is probably going to be something like a mutex. Yeah. So you can substitute mutex, you can substitute monitor. Okay, so so that's what happens. So what would we prefer? We would really prefer, as I mentioned, that we would like task 3 for the duration that it is preventing task 1 from running, for that duration somehow to have the priority of task 1. so that task 2 doesn't block things. That's something we want. It turns out that one of the NASA's most interesting episode back in late 90s happened precisely because of this bug. So this was a rover deployed on Mars, and it kept crashing. And, and basically, sort of, I guess, the public version of it was software glitches, too much work to do, and stuff like that. I mean, but the reality under the hood was that there was a situation exactly like this happening, where because of this priority inversion, a task was getting delayed. And so in this case, that task 1, for example, was getting delayed. And because task 2 was getting more work, as kind of loosely speaking, than they had thought it would. So in any case, since there was a task which was getting delayed and it was a critical task, so they actually had a watchdog timer for it, which would basically reset the system whenever that task would miss its deadline, because the idea was if this is a deadline, something has really gone bad, let's just restart the system. So what began to happen to this rover out there was that it would just repeatedly reset, and under the hood it was a problem. So the details are out here, but basically there was a higher priority task which was uh, uh, blocked by a lower priority task. So these are the task names in the code. It had grabbed the shared resource and was preempted by a medium priority task, exactly the scenario that we could have laid out. And the high priority task wasn't finishing in time, and then there was an even higher priority task which would periodically check that whether this task had finished or not. So it was kind of a supervisory thing, and it would see, oh, this thing is missing its deadline, there's something wrong, let's reset the system. And so that was a problem. And
Can you kind of fix this by assigning, in addition, priority to the task, to assigning priorities to the resources?
That's what you do. See, so roughly speaking, yes. And there are some other additional gotchas also. You also want to make sure you don't enter into a deadlock kind of situation. So there's multiple things you end up solving in the situation, but loosely speaking, yes. So how do we? So basically, apparently, this problem was noticed on Earth before it was sent, and I guess as usual of hardware versus software groups blaming each other. So that's what had happened. It was perceived as no importance because it was only affecting. It was thought some sort of science data gathering and all. In any case, they didn't pay attention. And then, as luck or bad luck would have it, there were more science data being collected. It turned out than they thought they would. So, upshot end result of all of this was that basically the way they resolved this thing was that they were running, they had a replica on Earth, and the OS they were running was this OS VxWorks, which I've mentioned a few times. It's really kind of a industrial grade RTOS, which is used in a lot of critical systems. And it turned out that it had a global flag that if you set in a running system, then all the semaphores in the system change their behavior to incorporate a technique called priority inheritance, okay, which usually kind of addresses this issue. So what they did was, from Earth, they essentially did an SSH or equivalent of that, and they changed that one global variable which affected the whole, changed the behavior of all the systems. So they were able to save the day, I guess. It wasn't caught because these kind of glitches, unfortunately, as you might imagine, depend very much on the sequence of events. Okay, so you may do a run and you'll never see it, and then suddenly you kind of see it. Okay, and so usually you tend to think these are hardware related. Okay, that's some hardware glitch and something. Okay, but so essentially wasn't. So apparently this whole episode, I mean, the reason it came to light was in kind of the main real-time system conference. Basically, talk from NASA which kind of describes this whole thing of what, or JPL rather, right? I mean, this stuff is all done by folks. JPL. So they kind of described all what happened and how sort of things worked out. So it was kind of an interesting. Okay, so let's take a break at 5 minutes before I describe how the mechanisms that solve this synchronization problems work. Okay, so 5-minute break. Okay, let's restart. So, so we saw the problem, and as was suggested, could we solve it by attaching priority to resources? And you'll see kind of bunch of different schemes came up. Some work, some don't, but uh, somehow you do have to begin to attach priority to resources as well. So to explain this, we're going to use a simple running example. So I have 4 processes, and we are only not going to ignore periodicity and all. We're just going to look at sort of one run. Okay. So I have, and what we have are 2 resources, Q and V, and then we have just normal execution E. So what you see out here is a trace for what these 4 processes want to do. So process at the top, L4, wants to do 2 time units of execution. Then it needs the resource Q and work on it for 1 time unit. Then V, work on it 1 time unit. And then again E. And the third, L3 is EVVE, so it executes a 1 time unit, couple of time units spent in V, and then execute, and so on and so forth. And moreover, they are not arriving simultaneously. So in this contrived example, L1 comes at time 0, L2 at time 2, L3 at time 2, and L4 at time 4. And we just want to see how the behavior changes in terms of when these tasks finish because of under different settings. Okay, so so let's start with the first case. So L4 comes at t equal to 0, and L4 is executing, and then L4, if you go back out here, needs Q. So L4 grabs Q. So let's see if we can get the controller.
L4 doesn't arrive at time 0.
No, L4 arrives at time 0. Sorry, I'm sorry, L1, the bottom one, L1. So L1 arrives at time 0, L1 needs Q, then L2 at t equal to 2, L2 and L3 arrive, L3 is higher priority, so it gets the CPU. So L3 starts running, executes, it needs the resource B, so it grabs the resource B at t equal to 4, L4 arrives, it needs 2 units of execution time, and so it gets it starts running. At 6, L4, after having done 2 units of execution time, needs one of the resources. It needs the resource Q. So at this point, it needs the resource Q, so it's blocked, so it stops running. So now remember, resource Q is with L1, but L3 being the higher priority begins to run, so L3 finishes with B, finishes with execution, gives them the CPU, L2 gets the CPU, L2 runs, only then L1 runs, finishes, and then control goes back to L4 and then execution. So as you can see, L3 and L2 managed to block L4 from proceeding because they had preempted L1 because they are high priority L1. So the deadline of L4 really kind of extended way into the future. And what you would intuitively like to accomplish is somehow during this period, then I would like to give L1 a higher priority than L2 and L3 so that L1 can finish quickly, or L1 can release the resource Q, and then control can go back to L4. That's what we would like to have. So one approach you can do in this case is explicitly priority inheritance, which basically says that L1 is going to inherit the priority of the resource. If the resource it is using, if it is blocking a high priority task, then during that time it will get a high priority. So at 6, since L4 is getting blocked, then L1's priorities will get bumped up and it's going to become the same priority as L4 so that it runs and then it releases Q at some point. At that point in time, L1's priority will go back to its normal self and L4 can begin to run. Okay, so that's what priority inheritance accomplishes.
Just a quick clarification. So in this case, can an equal priority thread interrupt an equal priority thread?
Normally, you would not have equal priority. Okay, but if you do, it would be it's an unpredictable. But all the analysis and these systems are designed with the assumption that you have a strict order interrupt. Okay, so that's what priority inheritance does, and what you would now another thing you would notice out here is L4 got blocked twice, once because of Q, and then again because of V, because same situation happened there. After doing Q, it needed V, but V was already locked by L3, so it had to give up the CPU. L3 progressed. Somehow it would have been not. So looking at this, as you can imagine, intuitively what may happen is if L4 used some k different resources, then in the worst case, it may turn out that it has to wait for each one of them because the lower priority task may have grabbed them. So ideally, even better would be somehow if we can prevent that from happening, in the sense that once I should get blocked once, but after that I should go kind of stop this race ahead. Okay, somehow avoid this repetitive blocking that's currently happening. But in any case, vanilla priority inheritance accomplishes this, and therefore the way you will analyze this thing is that going back to our good old response time equation. Remember, it was Ri equal to Ci plus interference, but now you also have this other term called blocking term. And this blocking term refers to how much time can I be blocked because of shared resources. And it turns out that the shared resources in this priority inheritance scheme, since I can get blocked once for every resource, so it's k equal to 1 through k, so I have uppercase k, that many resources, I can get blocked for each one of them. And the idea is that I can get blocked in all those cases where this indicator variable usage k comma I is 1, and I'm going to explain what that is, multiplied by the time spent in the critical section. And here we are assuming that the critical resource is such that whosoever uses it for a fixed amount of time, known fixed time, and that is CSK. So like for resource number 1, CS1 is the fixed time anyone using that resource needs. If you'll have to kind of modify this expression if different processes may use it for different amounts of time. Now, what is usage k comma I? So usage k comma I is an indicator variable, and it is 1 if the resource k is used by at least one process with a priority less than I, and at least one process with priority greater than equal to I. So, for example, going back out here, let's say I'm considering L2, and let's say considering resource Q. Resource Q is used by L1, so process of lower priority, and is being used by L4, a process of higher priority. So L2 can therefore be affected by it, and therefore usage for Q, the indicator variable for Q would be 1. So I have to account for that. That is L2's runtime can be affected by a lower priority task, and the reasoning simply is because in priority inheritance, now L1 for a time can inherit the priority of L4, and therefore, as you see out here, L2 is being blocked. Okay, so there's a blocking term which is coming, which we have to factor that in. So every resource, so when you are looking at how much a task can be blocked, every resource which is used by a lower priority task and a task of priority same as me or greater than the task under consideration, I have to factor that in. So we basically introduce this term, but this is a known constant term. I mean, this is purely a function of the way the code is, and you have to plug this amount here. One thing to be aware out here is to be able to do this analysis. It's very important that I know usage k comma I. And so what this means is that I have to somehow make sure that the code which is being the code which corresponding to the process declares upfront what shared resources it needs, because I have to do this analysis at the time I am letting a task into the system. I cannot simply have a task suddenly decide, oh, I'm going to use resource queue, because by that time it's too late. So it has to be declared upfront so that you can do this analysis. Not all operating systems provide this capability. I mean, if you look at, let's say in Linux, there are semaphores, but the way you use semaphore is deep inside. At any given point in time, you can declare a semaphore and start using it. Somehow you have to kind of upfront declare it. So it requires some additional API support to be able to pull off this kind of analysis, which again, systems that provide priority inheritance and all would have a mechanism to do it, which is at the thread creation time, you would supply the OS with some request that I need access to these semaphores somehow, okay, or other shared resource. Okay, so the problem, okay, so looking at this, the problem, as you can see, is the sigma term, right? I can be blocked on every resource. In fact, I may not be using any resource at all, right? The thread that I'm considering. It's just that there are a lot of resources in the system, and they're being used by someone which is lower priority than me and someone who is higher priority than me. So no fault of mine, but lots of blocking. So could we do it in a way so that instead of the summation, I can be penalized only once? And that's what happened with something called priority ceiling protocols, and they were kind of the main solution that emerged to this problem. And they are tricky to implement, so you are not going to find them in most operating systems, but VxWorks or sophisticated ones kind of go implement these things. So priority ceiling of a shared resource is the highest priority of all the tasks that may use that resource. So this goes to the concept that I was pointing out, which is, can I assign priority with resources also now? So that's exactly what's happening out here. So thus far we had talked in terms of priorities associated with tasks. Now we are going to say that there is a priority associated with the semaphore, or specifically priority ceiling. And priority ceiling of a semaphore or any other shared resource is the highest priority of all the tasks that may lock it. And then kind of the idea is that when a task attempts to access a shared resource, it will be suspended unless its priority is greater than priority of all the semaphores currently locked by the tasks other than tau. Okay, so there's circuit is out here. So let's imagine I have a task which is trying to execute a critical section. So let's say the critical section is free. So normally we would just proceed with it. But what this rule says is that no, you can't just go ahead and grab a resource just because it's free. You have to do an additional check. And that additional check is the following. Are there other semaphores in the system which are currently locked by a task? Then I have to make sure that my priority is greater than the priority of those semaphores. Right? So even though the semaphore I needed, the resource I needed is free, I'm not going to proceed with it if there exists some other resource in the system which has already been locked and whose priority of that resource is greater than my priority. Why did you think that? What problem are you trying to solve?
So that if those semaphores, when they release, probably they can use this resource.
So that those semaphores, when they are released, they can use this semaphore. Like who can use this semaphore? Who can
Those tasks that have higher priority.
Right. So yeah, so you're right. So the problem we are trying to avoid out here is the following: that those semaphore, let's say there's some other semaphore which is currently locked, and it has a priority ceiling which is higher than my priority. That means there exists some other task which may need that semaphore. and I don't want to come in a situation where I prevent that task from running. So I'm not going to proceed. Moreover, by not locking my semaphore, I'm also leaving open the option that that other task can take my semaphore. I don't want to enter into a deadlock situation where I have grabbed this and now that task needs this other semaphore. Okay, so we also want to avoid any deadlock situation. So we're being very cautious. We're saying we will proceed only if we know for sure that I will not cause a deadlock and that I will not cause some other task to wait upon, some other higher priority task to wait upon. So all of that is being handled in this crucial step over here. So even though the resource I need is free, because of what else has happened in the system, I'm going to be cautious and not proceed. And we basically say that if a task is unable to enter, use the shared resource for this reason, then the task which was holding the lock on that other semaphore, which had a high priority ceiling, is set to be blocking this task, and it inherits the priority of this task. Okay, so at that time, the moment a task decides not to proceed because of this reason, then that other task which had grabbed that high priority semaphore, it will inherit the priority of the task that I'm dealing with. Once I show the example, it will be clear, but multiple problems are being solved in this thing, and there are a couple of variants of this basic idea that exist in the literature. They go under the name of original protocol and immediate protocol. Net result of both these schemes, the difference is there, that number one, a high priority process can be blocked only once by a lower priority process. So instead of that sigma, it becomes a max. Okay, so that helps. There are no deadlocks, and then you don't have this transitive blocking that A blocks B blocks C kind of chain forming. So it doesn't happen. And meanwhile, what we want, namely mutually exclusive access to the resources, is maintained. So that property is maintained, but a lot of other good things kind of follow from this thing. So let's look at the two examples, how they work out. So let's imagine that I have two tasks, task 1, task 2. There are two shared resources, S1 and S2. And what task 1 is doing is locking S1, then it's locking S2, then it's unlocking S2 and unlocking S1. And task 2 does it in exactly the reverse order. Now, this example is structured to elicit the deadlock problem also, because as you might imagine, if I let task 1 lock S1 and task 2 lock S2, then neither one of them can proceed. So you want to avoid that. So assume here that task 1 is higher priority. Now S1 and S2, both of them are shared by both. So therefore their priority, the priority of the shared resource, is going to be that of task 1, right? Because of the higher priority conditions. So both S1 and S2 have priority of task 1, and task 1 itself is higher priority than task 2. So what will happen in the system is the following. Let's say task 2 is released earlier, so it executes, at some point it locks S2. Then task 1 arrives, and since task 1 is higher priority, so at time 2 when it arrives, it starts running. At some time later, it attempts to lock S1. But remember, S1 priority ceiling and S2's priority ceiling, both of them are tau 1. So at this point, S1 is free. So normally in a normal OS, you will say, okay, let's go ahead. S1 is free, let's go ahead and lock it. That's what will happen in Linux. But we don't want to do that. Instead, what we'll do is we'll say, okay, is there any other resource in the system which is currently locked? Answer is yes, S2 is locked. Does that resource have a priority greater than or equal to me being tau 1? Answer is yes. S2 is locked and its priority is equal to me in this case. And therefore, we will not proceed. Even though S1 was free, we will not proceed. Moreover, task 2 is the one which is holding the lock on S2. Therefore, task 2 will get my priority because the priority of task 1. So it will run. It will also lock S1, release S1. All of that magic will happen, and then okay. So in this case, this is a simple example. Deadlock got avoided. Okay.
So even if, for an example, you have n resources that can be locked. You can only have one locked at one time.
No. You can have multiple resources being locked. That's
Oh,
not an
just
issue
one.
because they could be entirely independent sets. So that's not an issue.
Or you can only have one if it's higher.
You
or
can
equal.
only be blocked with this. You can only be blocked once. We'll see the formula shortly, but basically, you won't have this repetitively where I'm blocked, release. Okay, I'll face it only once. Yeah.
So what if task 2 doesn't use the S1 lock and instead it locks S2 again?
What did you have in mind? Like, I mean,
Task 2 locks S2 again,
while it is it releases it and
then locks S2 again.
yeah, but the moment it releases it,
Yeah.
then control will go back out here, right? So then this guy will run. Remember, task 2 has the high priority only as long as it was blocking. So the moment it releases S2, task 2's priority task 2 will no longer be blocking task 1, and therefore its priority will go back to its original self at task 1.
So this is assuming, like, in all these cases we've been talking about, there's no OS that has a regular period of like thread switching where like it forces threads to switch. This is like
Regular period of what?
so in this case the second or task 1 just happened to run at that time, so it interrupted because it interrupted task 2.
Yeah, I mean it's some arbitrary time, but for purposes of example, I structured it so that it happens while task 1 is already established.
Right. Would this be like always induced or just
No, but let's say at some magical time it happens during the run. Because remember, task 1 may be periodic, task 2 may be periodic. In some run of the system, the arrival times will differ. Also, the computation time may be affected by caches and stuff like that, right? So it may very well happen that when task 1 arrives, it so happened that task 2 was blocked. And OS really can't do much about it in the face of all the variations that take place. So you can go by and not face this issue at all for a long number run. And there are papers which, given the task structure, talk about the probability with which you are going to enter into the thing. So it's not like, in every run you're going to face it, and at the same time, it's not that you are not going to face it at all. In fact, some post facto analysis on the NASA thing quantified the probability that with which the system would have failed. But all that theory and all the more subsequent to the failure. So, any other question? Okay, so that was a simple example. The two main protocols that exist, the original and the immediate, so they have slight differences. So in the original protocol, each process has a static default priority, the way we assign in the OS. Each resource has a static ceiling, which is the maximum priority of all the resources that use it. So essentially the processes declare upfront what resources they're using. We compare all of them and then give each resource a priority. Then process has a dynamic priority. And the dynamic priority of a process is the maximum of a static priority, and any it inherits because it's blocking a higher priority process. And then finally, a process can only lock a resource if its dynamic priority is higher than the ceiling of any currently locked resource. This is exactly what we had previously. Okay, so, and in that case, with some sort of thinking, you can show that I can only be blocked once, and for k resources in the system, and then I should only consider the worst case resource, the one which has the highest value whenever I use the resource. So the BI turn, where previously it was a sigma, now becomes a max. So big improvement. So in our example of the 4 tasks, the way that works now is I have 2 resources, Q and V. Q is being used by L1 and L4, and V is being used by L4 and L3. The static priority, so the priority ceiling of Q and V are therefore going to be the same as the priority of L4, right? The highest of the 2. In this example, L1 starts running, it uses Q at t equal to 2, L3 arrives, it runs, and then it attempts to, at this stage, L3 attempts to lock V. But remember, even though V is free, we will not let it lock V. We are first going to examine, is there a resource in the system whose priority ceiling is higher than L3's priority and is currently locked? And the answer is yes, Q is there in the system, it's already locked, and therefore L3 will not let L3 proceed. And the way we will not let L3 proceed is because at this stage, what is happening? So we will not let L3 proceed, and at this stage, because L1 is blocking L3, therefore L1's dynamic priority will become that of L3. So from t equal to 3 onwards, L1's priority is that of L3. So now L1 runs. At t equal to 4, L4 arrives. Its priority is higher than even the dynamic priority of L1, so it continues. At t equal to 6, L4 attempts to lock Q, but Q is already booked. So now L4 blocks, it cannot run. L1 again becomes the highest priority process which is able to run. So L1 runs. At t equal to 8, it releases Q. Now things go back to L4. L4 uses Q, uses V, releases, only then control goes to L3 and then finally out here. Looking at this, comparing with the previous example, you would see that L4 is being blocked only once, whereas with just plain priority inheritance, it was being blocked 2 times, one for each resource. So as you would desire in this case, L4 therefore becomes the soonest possible. Given that Q was already locked, you cannot really do better than this. Okay, so that works out in our the way we want it. ICPP came later, immediate priority ceiling protocol, so IPCP. Okay, so in this case, each process has a default priority, again as before. Each resource has a static ceiling, again as before. A process has a dynamic priority, that is the maximum of its own static priority, and the ceiling values of any resources it has locked. So remember in the previous one, the dynamic priority was if I was blocking a task, whereas here, the moment I lock a resource, I get his priority ceiling. In particular, in this case, going back out here, the moment L1 locked resource Q, L1's priority becomes that of the resource. And therefore, the way things work out is L1 executes, locks Q, Q's priority ceiling is that of L4. Therefore, at this stage, L1's priority becomes that of L4. So now when L2, L3 arrive, they don't even get the CPU. In fact, even when L4 arrives, it doesn't get the CPU because this guy is currently running and L4 priority is higher. So L1 finishes and then kind of rest of the stuff follows. So this is this is the immediate one. It's kind of more aggressive there. Its behavior is the same in terms of the worst case analysis. That is, the blocking term value remains the same. It's just that it's easier to implement. I don't need to have to figure out that the dynamic priority of a task depends upon the priority of the task who has blocked a resource. Okay, in this case, I just keep track of what resources I'm using, and every time I lock a resource, I use its dynamic priority. So ICPP leads to fewer context switches, easier to implement and stuff like that, but worst case thing is the same. Let's see. So the real sort of hard real-time systems, which so VxWorks and a few others like that, they implement these more sophisticated variants around it. Okay, and they kind of take care of a lot of issues, as you can see. You will not find in the simpler OSs, maybe you'll just find priority inheritance. But as you see, priority inheritance alone does not safeguard you from deadlocks, and also it only it doesn't promise you minimal blocking. You can block once every resource. So the better OSs will provide you one of the ceiling protocols. Many operating systems don't provide anything, so there's no priority inheritance either. so they obviously remain susceptible to this, these kind of issues. In general purpose OSs, you won't see this at all. Okay, so next thing before we run out of time today, other considerations that enter into picture. So oftentimes your tasks, their arrival time is not strictly periodic, or what I mean by that is it's jittery. So it's nominally periodic, but because of delays in the outside world, maybe they're arriving over a network, these are video frames coming over a network or something, there's jitter in them. So the network, so the promise you have been given is your task arrive every time t, but there might be some plus minus delta around it. That's the jitter. And the way you deal with this thing is that you add a jitter term to the response time. Okay, so our equation becomes as shown out there, where you would see that this response time inside the ceiling has a j sub j term in it. So the idea is that in the worst case, the high priority task which are interfering with me may see some jitter, and therefore they will affect my response time. So you're taking that in. This is something that one should factor in, particularly in a network setting. It's also possible that the task is being activated periodically as a result of an output of another periodic task. Maybe I have one processor where I'm running a rate monotonic system, priority-based system. Its output is going over some link to another processor where again I'm running something. So now if you think from the perspective of the second processor, its periodic tasks are arriving because of what's happening on the first processor. And as we discussed a bit earlier, the only guarantee we make is you'll finish by the deadline. So on first processor, the only promise we are making is you're finishing by a deadline. We are not making any promise about where in the period you are finishing. So if I were to examine the output of the first processor, its output for a given task may be jittery from one instance to another. So I can factor them this way out here. Is there any other way you can handle jitter? So one is, yeah, you have to trust me, this formula magically accounts for it. But how else can you handle jitter, jitter problem? Packets arriving. So jitter is often also called delay variance. Okay, my delay instead of being fixed varies.
You can buffer.
Exactly. Yeah. So you buffer. So the idea would be that the receiver or the transmitter, well, if the delays are happening over the network, then kind of buffer before you handle them. What's the disadvantage of buffering besides needing a buffer? Even any thoughts? What?
Initial delay.
Initial delay, a fix, yeah, because it may happen that on that run I was lucky and the jitter was actually very tiny or non-existent, but since I have to put in the delay with some worst case jitter in mind, so I have to kind of do
So like the buffering would kind of just exchange an arbitrary jitter for just a constant delay.
Very common thing is you say, you know, worst case delay can be this, and therefore I'm going to account for that. Okay, so what I'll do is I'll put some sort of a timestamp on the packets, but play out when certain time has passed. Okay, so that's the initial thing. So a very common place you'll encounter, like on YouTube or stuff like that, you often see buffering message, right? That's exactly what's happening. Now, these schemes are a little bit smarter than the way I'm suggesting, because what they also do is they'll start out aggressively. They'll say, okay, you know, I'm being optimistic. It's a good network. Okay, and then, or maybe they might do some probe packets back and forth to get an estimate of the delay, set the buffer size accordingly, but then if they start running into a situation where the buffer underrun is happening, then they increase the buffer. Okay, so that's how you find that. So there are, again, lots of papers examining these different mouse schemes and stuff like that, but the basic concept remains like this. So jitter is kind of a source of problem, obviously. Another issue which we didn't address explicitly, but I would, in the remaining time, I would like to do that, which is arbitrary deadline. So thus far, I covered two cases: deadline equal to period and deadline less than period. But deadline can be greater than period also, right? I mean, I can basically say my task comes every 10 seconds, but every time my task comes, you have up to 20 seconds to finish it. So in that case, more than one copy of the task may continue in the system, okay? Often happens with, right, I mean, my underlying signal may be a very rapid dynamic signal, but latency tolerant, okay? So I can deal with that. So we already saw how to handle d less than t and d equal to t. Those are handled. But d greater than t has a complication. The complication is that I don't have a theory to say what assignment is optimum. I cannot say it's deadline monotonic. And the complication arises because I may have multiple copies of the task existing in the system, right? So I may not be done with the current copy and a new copy of the same task has arrived, okay? And they will, so there's obviously some coding issues around it, but the deeper issue which comes up is that I have to do a little bit of further look ahead. So let's look at an example. I have two tasks, task 1 and 2, computation time 28 and 80 and 71 and 110. Okay, and let's say for sake of example right now, all my deadlines are infinity. I just want to look at the response time. So in this case, what happens is, let's look at response time for task 2. So we have given higher priority to task 1, and now I'm looking at how task 2 behaves. So task 2, one copy comes at 0 along with a copy of task 1. Its completion time is going to be 127, and that is simply because if I go back, its computation time is 71, and it needs 28, so two copies would arrive of this, so 28 plus 28, 56, plus 71, 127. So it turns out that the first copy of the task 2 will finish at time 127. And let's say I gave you a deadline of 127. So you say, okay, you know, it's good, I'm done. But let's see what happens to the future copies. So remember, its period was 110. So at 110 to 23, 30 more copies will arrive, and meanwhile, copies of task 1 are also arriving. If I look at their completion time, it would be like this. If I look at the response time, first copy had a response time of 127, next one 116, third copy 133. It actually went up. 122, 111, 128, 117, and then back to 106. And after this, the system is effectively restarting because 106 is less than 110. So now I'm back to a situation where I have only one copy of the task in the system. But looking at this, the worst case deadline is actually worst case response time is actually 133, which means that if my deadline is desired deadline is less 133 or less, then this system is actually not going to work. But if I had only looked at the first copy and its response time, then I would have falsely declared it to be schedulable. So in this case where response time is more than the response time is if the deadline is more than a period, one has to examine multiple iterations until my response time goes below the period. Okay, and only then I can start. So this complicates our formula a little bit more because I can no longer say it's the first instance with the one which arrived at t equal to 0 that I have to look at. I actually have to now analyze all the instances. So there is an additional factor q which indicates which instance we are looking at. So we are going to start with q equal to 0 to look at the initial instance. And then I'm going to keep increasing for q equal to 0, 1, 2, 3 until I find a response time which is less than the period. And then I'm going to go back and say, did any of those response times exceed it? Okay, so I have to really sort of unfold at time, so my complexity goes up even more, but that's what we have to do out here. So important thing that for systems where latency which you require, the deadline that you have is more than the period, then there is no theory. You have to try all possible priority orderings, okay, and then just the hard way verify that does any of them.
Is it possible that you just never get something that's less than the period, and then you give a bound, but it might still work. Like,
Well, in a given run of the system, anything can happen, right? So the part to remember is that we are designing these systems so that we are robust to all possible arrival times that may happen. So I think in a system where I can control precisely at what time the periodic tasks are coming relative to each other, then I can statically schedule. But what's happening in these systems is we are designing them so that when the system powers up, we don't care about precisely when the first copy arrives, although we know from that point on it's periodic, but we want to be able to make the promise that irrespective of the phase of the task, namely when the first copy arrives, we can also always schedule. Okay, and that's simply because there are always minor variations. Okay, so let's continue on Wednesday.